Welcome. This is a question exploration routine for an area accumulating function. So if you want to turn into your books, this is AA number 1, free response number 1. So here's the graph, and it says the graph of a differentiable function. So remember, this is the time that we are writing down key terms. So my first key term would be differentiable. And my question here is, what do I know about differentiable? What does the differentiable tell me? It tells me two things. The first thing it tells me is that the derivative exists. And the second thing it tells me is it tells me that the function is continuous. So if the derivative is, if the function is differentiable, that's what we've got. All right, and then I see that there's a closed interval. Okay, closed interval, anytime I see a closed interval. Now they specifically worded it closed interval. That was really sweet of them. That is not what they're always going to say. So when I see this, that is one indication of a closed interval. This is another way they could write it. So here they have told us this 3 times, in words, in interval notation, and in an equality notation. But on this I want to look out for, and those are our theorems, extreme value theorem, intermediate value theorem, and mean value theorem. So I think that I'm going to stop here at the moment because these have generated several things that I need to know. Extreme value theorem is going to involve mins and maxes. So if I see any mins or maximum words, then I should be thinking extreme value theorem. Intermediate value theorem involves y values. Mean value theorem talks to us that the slope of a secant, which is algebra 1 slope, equals slope of a tangent, which would be the derivative. So that's just what that kind of brought to mind. All right, continuing, what do we have? We have as shown above. All right, let h of x, so let's look at this function. All right, this function h of x. So I'm going to put down my function right here. And it's the integral from 1 to x of f of t dt. All right, so the first thing I know is that this is an area accumulating function, and I'm on a graph, so I will probably be having to do area accumulating. This also tells me that the placement of f of t tells me that f of t is the derivative, because it's on the right side of the integral, which means I'm going to come up here and I'm going to write real big that this is a derivative graph. It's important that we know what we're looking at. Another thing that I want to do, and I'll probably just highlight, is I'm not starting at 0, I'm starting at 1. But then again, when I look at my graph is also starting at 1, so we're okay. So this is an area accumulating function, meaning that f of t is the derivative. All right, so now let's look at h of 1. So if I want to look at h of 1, that means that I want to know the y value on the h function at x equal 1. So that means I'm going to do h of 1, which means I substitute into my integral f of t dt, and that means I'm looking for area. Now that's kind of an easy one, and we'll talk about that later. All right, so now I have h prime of 4. What does h prime of 4 mean? So h prime of 4 means I have to find the derivative of h. And if you recall, h prime of x is going to be the derivative. I have 1 at the bottom. The derivative of x is 1 times f of x. So h prime of 4 then basically means I'm looking for f of 4. So the derivative of 4 is going to be the y value of f from what I see. Here I will actually have to find, and I probably should alternate colors. I'm actually going to be substituting in, and I'm going to be finding area. Here the derivative tells me that basically I'm looking at the y value on the f function. All right, on what interval or intervals is the graph of h concave up? All right, so concave up. What do I know about concave up? Concave up occurs when the first derivative is increasing, or where the second derivative is positive. That's how we look at concave up. Justify, so I have to remember to explain. So we've got to put justify in here, and that means we're going to have to explain. All right, and then looking at the last part, what does it tell me? It says find the value of x, so that's important. I want x, at which h has its minimum. All right, key word here would be minimum. Okay, first of all, this is the minimum of h, not f, okay? And when I'm looking at minimum, because it said closed interval, all right, we were on the lookout earlier, I am looking at extreme value theorem, which means they occur at critical numbers or endpoints, and this is what everybody forgets, is the endpoints. Okay? So justify your answer. Okay, so I think that maybe I should talk about critical numbers again. Critical numbers is where the derivative is equal to 0 or undefined. So I think I've gotten pretty much all my important words. So I know I've got a derivative graph. I know I'm looking out for special theorems, and this one down here says it's probably going to be extreme value theorem. This tells me that I'm going to be substituting into my function, which means I'll be finding area. This tells me I need the derivative, which I found, and I'll do it again. And this tells me concave up. I'm either going to be looking at increasing, decreasing, or positive, negative, depending on what my graph is. So from here, we're going to go to the next stage of the problem, and this is where we are going to actually solve the problem. So I'm going to go to my AA, since I'm going to not be able to see it. So my area accumulating, I think I will work with, I might want to copy this graph. I think I'm going to need this graph. So let's see, copy, we're going to come to the next page, and we're going to paste. All right, so here's my graph over here. All right, so part A, this is where we're going to start to work on this. Part A says find h of 1. H of 1 means that I'm going to have to substitute 1 in for x, which means I'm going to have the integral from 1 to 1 of f of t dt. Now what's special about this integral is we should be able to do this on properties of integrals without even having to look at this, and it would be 0. If this was not 0, then I'm going to be looking for the area under the curve in order to do that. So we know h of 1 is equal to 0. Okay, the second part, did they ask us to justify? It says no. So now I want to find h prime of 4. And again, it's so important that you all actually do the derivative of this integral. So the derivative of the integral, if you recall, this was an x before we substituted. It's going to be the derivative of that upper limit times f, and we substitute in. So my h prime of 4 becomes f of 4. So I'm going to come over to my graph. This is 1, 2, 3, 4, and the y value is 2. So that is equal to 2. And again, they did not ask us to justify. So now we're going to go to part C, and now part C is going to require some work. It says, on what interval or intervals is the graph of h concave up? So I want to know when h is concave up. Now we talked about that concavity works with first derivative increasing or second derivative being positive. So we marked this on the previous page that this is a derivative, and I should say first derivative graph. So since I'm looking at the first derivative, it makes sense that I should choose this part of my concave understanding. So I want the intervals where this graph is concave up. Well, I can see that beginning at 1 and stopping at 3, my graph is increasing. Now 3 all the way to, and I don't think I did this very well, this should be 6, we're decreasing, but notice that 6 to 7 we're increasing again. So that means on these intervals, h of x is concave up. Now they've told us to justify, and you've got to be very, very careful here. And I'm going to say because h prime of x is increasing. Positive doesn't work because that's 2 derivatives away. Now, another way you could have said it is you could have said because f of t is increasing. Because f of t is the derivative of h. So either one of those would be correct. So I have given the intervals, and I have justified. So I'm ready for part D. Now part D says find the value of x. So I'm looking for x. Important that you make notation of this so you make sure you answer the question. And I'm looking for a minimum. So I know that it's either going to occur at the endpoints or it's going to occur at the critical number. So my endpoints, and let me get a different color, get light blue. My endpoints are, so I think what I'm going to do is I'm going to say candidates. The candidates are at x equal 1, that's an endpoint, x equal 4, because that's a critical number where the derivative equals 0, or at x equals 7. Now I know h of 1, we found that earlier, h of 1 is indeed 0. So we know that. All right. Now, because this is a curve, if these were straight lines, we literally could find h of 4 and h of 7. But this is going to be a little bit more convoluted because we have to think through this. So what is happening? The area under the curve, this is a derivative graph. So if I were to look at h of 0, so if we look at, I'm sorry, 4, what do we know? We know because this graph is above the x-axis, I've been increasing until 4. And because that's below the x-axis, I've been decreasing over to 7. This is 1. So, because I went increasing to decreasing, that means that h of 4 is going to be a maximum. And it's going to be a maximum because h increased and maybe I should say h of x increased from x equal 1 to x equal 4. and then begins to decrease. So this is what I mean, that you kind of got to write it out in words. It's not as clear cut as if we could have found the area. Begins to decrease. So the maximum is at 4, but that's not what they asked us. But what that does tell us, maximum is at 4, not a minimum. All right, so we have determined that it's not 4. All right, so now the minimum is either at 1 or it's going to be at 7. Now think about this. The area under the curve is much greater from 1 to 4 than it is from 5 to, and actually I think I did this wrong. 1, 2, 3, 4. This is 5. So yeah, you've probably already seen this. No, that was right. Just kidding. Somehow I feel okay. So anyway, all the way over to 5, our function is increasing, and from 5 to 7, the function's decreasing. But because this area is greater than this area, we have not decreased past the lowest point. We start at 0, we increase, and then we come back down a little, but we have not decreased enough to go beyond our starting point of 1, because the increase area is greater than the decrease area. So that is what I'm going to write. I'm going to say the minimum occurs at x equal 1 because the area under f of t from x equal 1 to 4 is greater than the area from x equal 5 to 7. And I'm sorry, this is where I should have a 5, from 1 to 5, is greater than the area from 5 to 7. So the y value at x equals 7 is higher than the y value at x equal 1. And then I'm going to add extreme value theorem tells me this. All right, so had this been a problem where you literally could have computed the area, you wouldn't have had to write all this. You literally could have said h of 1 equals 0. You could have figured out the area from 1 to 4, and you could have found the area from 1 to 7 and figured out which one was the smallest. But unfortunately, it wasn't that way because of the curves. They didn't ask us we couldn't find those exactly. All right, so then, what is the main idea or answer? We did the A, B, C, D. I'm going to put C number 3. So now some common mistakes. Missing the EVT, forgetting the endpoints, could be our candidates for max and min. That's one common error. Let's see, confusing h of 1 with h prime of 1, or h of 4 with h prime of 4 is a common mistake. Confusing concave up for first derivative with positive, negative versus increasing, decreasing. That's another common error. So that is my QER for an area accumulating problem.